Hi boys and girls, this video comprises the lecture for vector-valued functions. As you know, it's not a topic that is in your textbook, but it is on the AP exam. So this one video is I'm just gonna hit the highlights as far as what you need to know for the AP exam. The two packets that I gave you prior to spring break, as I explained to most of you, one of them is just basic vector information. If you've never dealt with vectors before, you don't know what they are, and you might want to go through that just to look and see what is a vector, how do I add or subtract them, or what are the dot products or cross products, or magnitude, direction, etc., etc. All of that is basic vector arithmetic, which is not what will be tested on the AP exam. What will be tested on the AP exam, of course, is the calculus that you can do with vectors, derivatives, integrals, etc., and those applications. So the second packet that I gave you, which I believe starts with the topic vector-valued functions or vector functions, within that packet is the information that I am laying out for you here in this lecture. Now this lecture isn't going to correspond exactly with that packet. Use that packet as sort of a reference for the formulas or possibly additional examples. I did take this particular screenshot out of the packet, but for the most part now I'm just going through a few formulas, a few examples to get you used to what you're going to be seeing on the AP. Now also, there's not a homework assignment at the end of this lecture in the traditional manner that we're used to, where there's a page number and problems assigned, because of course we're not doing homework out of the textbook. But I will be posting on Edmodo the assignment that will be associated with this lecture. So let's get started. A vector-valued function is a function of the form. Notice we have the little arrow on top indicating that it's a function. And then you have these sort of angled grouping symbols, x of t, y of t. X of t and y of t are two different equations with respect to t, a horizontal component and a vertical component, very much like parametric equations. Anyway, this is a vector-valued function. Since x of t and y of t are functions of the parameter t, the vector-valued function has many of the same properties as parametric functions. They are very similar, and a lot of the things that you have already learned about parametric functions are going to apply here as well. Another way to represent a vector-valued function is in terms of its unit vectors, I, little hat, j hat, whatever you want to call this. I is the horizontal unit vector and j is the vertical unit vector. You'll see in your packet, if you look there, that they also show three-dimensional vector space, but we're going to restrict our discussion to two-dimensional vector space here because, once again, that's what we'll be doing on the AP exam. If there were a third dimension, it would be k hat, the unit vector for the third dimension. But therefore, we could write this equation or this function like this, and it means the same thing. Our vector-valued function r is equal to x of t, some function, horizontal component function in terms of t, times the unit vector I, plus some y function in terms of t, which is a vertical component, times the unit vector j. So I want you to be familiar with both notations because they will both show up, and I'm not sure exactly what you would see on the AP exam. Now, just to get us started, here's an example of a vector-valued function and its graph. Notice that the x component, the x of t is t, the y component is t cubed minus 10t plus 7. Here are some evaluations at time equals -3, -1, 1, and 3. Plugging those into each of the functions, you get these ordered pairs. -3, 10, -1, 16, 1, -2, 3, 4. So at the function when t is -3, this is the ordered pair, -3, 10. Now, notice that these little gray arrows which are drawn here are called position vectors. Every position vector represents the position of a point in the coordinate plane. Each of the ones on this cubic, if we actually took every time interval and evaluated the function at every time interval that we possibly could, we would have unit position vectors pointing to every single point on the curve, and you could see that the curve, of course, forms this cubic function. Position vectors extend from the origin and then they terminate at a point in the plane. In this case, they would be terminating at -3, 10, -2, whatever that is, -1, 16, etc., etc., you know, the ones that we have evaluated here plus a few more. Now, you might think, oh, well, it's so easy because r of -3 is the x component. Well, for this vector valued function, the x function was just t, or x. In other words, the x values were the t values. But of course, that's not always the case. We could have had something like r, a vector function in r maybe would be something like this. What if it was t squared, or t squared plus 1? And then you had t cubed, you know, blah, 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 whatever. The point being that for this example, yes, the x-coordinate, or the t that we were evaluating, was the x-coordinate of the point. But that's not always the case. And usually the times that you are evaluating at will not be one of the coordinates of the points that result in your vector. So FYI, that's just a little brief introduction to vectors. Now, on the next slide, we're going to do something that should be similar to us because we did it with parametric equations. We're going to eliminate the parameter and convert the vector valued function into an equivalent function of x. Rather than two functions in terms of t, we will convert this to a function of x. So essentially what we have here is x, or x of t, is t plus 5 over t. And of course y, or y of t, is t squared over 2. Now once again, we're going to solve for t in one of these equations and then replace t in the other equation with that expression. I'm going to solve for t over here. And so first of all, just cross multiplying gives me xt equals t plus 5. If I subtract the t over and then factor out the t, oops, that should be x minus 1 equals 5. Dividing both sides by x minus 1 would give me 5 over x minus 1. So now let's replace t here with 5 over x minus t, x minus 1. Sorry, getting ahead of myself here. That's x minus 1, dividing both sides by x minus 1. Okay, so back to replacing it now. We're going to have y equals 5 over x minus 1 quantity squared over 2. And let's simplify the numerator a little bit and say that that's 25 over the quantity x minus 1 squared over 2. But as we know, dividing by 2 is the same as multiplying by 1/2. So we could say that this is 25 over 2 x minus 1 quantity squared. So we have turned this vector valued function into a rectangular equation, just like we did with parametric equations, by eliminating the parameter. What else are we going to do with vector valued equations? We're going to find the magnitude of a vector. The magnitude of a vector is akin to the length of a segment, or the distance a particle travels. The formula for finding magnitude is a variant of the distance formula. This makes sense because if you think about it, when you're finding some sort of distance to a point in the plane, it's always the hypotenuse of a right triangle if you look at the horizontal distance and the vertical distance. And so, of course, finding the length of that hypotenuse is where the distance formula comes from. And so that's why this is also going to be a variant of the distance formula. So the magnitude of this function, vector function r of t equals this, is notated with double absolute value bar kind of looking things, even though this is not absolute value. These double bars mean magnitude. And we're going to do just something very similar to the distance formula, the x component squared plus the y component squared, and then take the square root. So let's do the magnitude of this particular vector function. And that means we're going to do the square root of 3t squared squared plus 1 over t squared, which simplifies to 9t to the 4th plus 1 over t squared. Now let's get a common denominator in here. In order to get this 9t4 to have a common denominator of t squared, I'm going to need to multiply that numerator by t squared also. So now I'm going to end up with 9t to the 4th, 6th actually, multiplying it by t squared, plus 1 over t squared. And even though the numerator isn't going to simplify, sorry, that should be 9t to the 6th plus 1 in the numerator, we can write this over t because the square root of t squared is t. And that is the magnitude of this vector valued function. Now, notice the second question says, what is the magnitude of this function at t equals 1? Well, obviously that's going to be easy to find. We're just going to replace t in our function with 1. 1 to the 6th power plus 1 all over 1, and this becomes, of course, the square root of 10. Now, if you had known that you were going to be evaluating the magnitude at 1 at the beginning of this problem, we could have found the value of r of t at 1. Oh, actually, I should have written this as we could have found the value of the function at t equals 1 and gotten the ordered pair 3, 1. Then you really wouldn't have to go through this process. You could just find the magnitude at 1 by using the distance formula with those coordinates, 3 squared plus 1 squared, which is also the square root of 10. So the moral of the story is, if they're asking you for the magnitude at a certain time, first plug that time into your two functions and get the coordinates and use the distance formula. Much simpler. But if you're asked for the magnitude of the vector in general, then of course you have to plug the functions into the distance formula and get sort of the function for the magnitude at any time. What else are we going to do with vectors? Well, we're going to take a derivative. Shockingly enough, that actually I have it already on here and I shouldn't. I think I was going through and seeing what I needed to do for each problem and forgot to erase that. But pretend like you didn't see it. To find the derivative of a vector function, first differentiate x of t and y of t with respect to t. The derivative of vector function r of t equals this is r prime vector t is x prime of t, y prime of t. So simple. So r vector prime of t is simply going to be 6t, and then when you take the derivative of t to the negative 1, we know that that is negative 1t to the negative 2, so it will be negative 1 over t squared. That's it. So easy to take the derivative, right? Just take the derivative of each component function. Now, how would we apply this? An application of the derivative of a vector-valued function is to find the equation of a line tangent to the function. Well, as I always say, when you're trying to find the equation of a line, you need two things, a point and a slope. Obviously, the slope is going to come from the derivative of our vector-valued function, but let's go ahead and find the the point first, because we're going to find the equation of the tangent line to this vector-valued function at the point t equals pi over 4. Well, what are the coordinates when t is equal to pi over 4? So essentially, we need to find out what r of pi over 4 is. And we do that by saying sine of pi over 4 squared, sine squared of pi over 4, and then cosine of 2 times pi over 4. Those values are sine of pi over 4 is square root of 2 over 2, and when we square that, we get 2 over 4, which is 1/2, and then 2 times pi over 4 is cosine of pi over 2. Cosine of pi over 2 is 0. So here's my point. I already know what this is now, 1/2, comma, 0. Now I just need my slope. So we're going to look for r, the vector r of t prime, r prime of t. I'm not exactly sure how to say all of this. And of course we know that that is just the derivative of each of the component functions. 2 sine t, we would have to use the chain rule here because this is raised to a power. 2 times this derivative, this function to the 1, times the derivative of that function cosine t, comma, and then of course the derivative of cosine 2t is negative sine 2t times 2, so that's negative 2 sine 2t. So now let's find out what we have at pi over 4, because that's going to be the slope at the point that we need. So this is going to be 2 sine of pi over 4 cosine of pi over 4, comma, and then negative 2 sine of 2 times pi over 4 is pi over 2. Okay, so as we work this out, sine of pi over 4 is square root of 2 over 2. Cosine of pi over 4 is also square root of 2 over 2. And then sine of pi over 2 is 1, so that's just going to be negative 2. Over here, square root of 2 over 2 times square root of 2 over 2 is 2 over 4, which is 1/2, times 2, which is 1. So we find 1, negative 2 are the x and y components at pi over 4 of our first derivative. Well, remember, what we need now is dy dx, which is equal to dy dt over dx dt. And we found that dy dt is negative 2, dx dt is 1, so that is negative 2. So here's our slope, and here's our point. Negative 2 is our slope. So I will find a space here in the middle. We will do y minus 0 is equal to negative 2, x minus 1/2 to write our equation of a tangent line, which is y equals negative 2x plus 1. And there you have it. Remember, when they ask for an equation of a tangent line, you need 2 things, a point and a slope. Using t equals pi over 4, you can plug that into the original equation to get the point. And then, of course, using pi over 4, plug that into the derivative to get the slope. What's next? Here are some other applications of the derivative. Vector-valued functions and parametric functions, by the way, parametric equations, by the way, are often used to describe particle motion. Common questions involve position, velocity, speed, and acceleration. So let's just clarify what these things are. Position function is just the original vector-valued function, and you might think, well, why do we need to say s vector of t when we have r vector of t? Well, s is commonly used to indicate position, so when we're talking about the application of position, we might use s instead of r. Velocity, as we know, is the first derivative of position, so that's going to be the first derivative of each of our component vectors. Acceleration is the first derivative of velocity, the second derivative of position, which will be the second derivative of each of our component vectors here, which would be x double prime of t, y double prime of t. Speed is the magnitude of velocity. So we would take each of the first derivative components, square them, add them together, and take the square root. So whatever we're finding the magnitude of, this is the formula that we use, but since in this case we'd be finding the magnitude of velocity, we would take the first derivatives and insert them into the magnitude sort of scenario. All right, let's see how this looks in an actual problem. Find position, velocity, speed, and acceleration of the given vector-valued function. Well, we know that s of t, when we're talking about position, it's not really going to be any different than what we start with, sine of t, t squared. Let's go ahead and do velocity then. It's going to be the derivative of sine, which is cosine of t. The derivative of t squared is 2t. And let's go ahead and skip down to acceleration as well, since we're kind of on a roll here. The derivative of cosine is negative sine t and 2. And then finally, let's do speed, which is, of course, the magnitude of the acceleration vector. And that's going to be the square root of cosine t squared plus 2t squared. Now, not much simplifying going on here, but of course you can write this as cosine squared t plus 4t squared. And there you have it. Now let's do another example using these principles. The given position function describes the path of an object moving in the plane. Find velocity, speed, and acceleration of the object at the point 8, 4. Okay, so now we're going to do the same thing that we did before, but instead of just general formulas for velocity, speed, and acceleration, we're going to find exact velocity, speed, and acceleration of an object at the point 8, 4. Now, I'm sure that you can't help but notice that our velocity function is given in terms of t, but these are x and y coordinates. So we're going to need to figure out what t corresponds with the point 8, 4. We have these two equations to help us. T cubed, the x component has to be equal to 8. T squared, oops, I didn't mean to write that equal sign there. T squared, the y component, has to equal 4. Now, if you solve for t here, you get plus or minus 2. But when you solve for t here, you just get 2. So they both need to be the same time. Therefore, we know that 2 is the time at which the point 8, 4 is occurring. So let's go ahead and take our derivatives. We have velocity of this function. Notice, just for fun, I wrote this like this so that you don't forget that this is another way to represent the vector function. And we're going to be using this in a moment, so I wanted to bring it back and just say it could have been written this way, but you just need to know that the coefficient of each of these unit vectors is the function that you're dealing with. So the velocity function here is going to be 3t squared, 2t, or this could be written this way, 3t squared, just going to say I hat or I unit vector, plus 2t j unit vector. Exactly means exactly the same thing. At the point 2, or t equals 2, we have here that this is going to be 2 squared is 4 times 3 is 12, 4. So that is velocity at t equals 2. Now let's do acceleration. Again, it just seems to flow more naturally to do acceleration next. We know that that is the derivative of velocity, which is 6t, 2. This could be written as 6t I hat plus 2 j hat. Same thing. And if we want to find acceleration at 2, that's going to be 12 2. And finally, let's go ahead and do speed, which is the magnitude of velocity. Now, we first, since we already have these components, 12, 4 at 2, we don't really need to use the functions themselves. We can just say, well, what was the speed at 2? Since I already know the velocity is 12, 4, I can just say 12 squared plus 4 squared, which is the square root of 144, plus 16, which is the square root of 160, which is 4 square root of 10, 12 something. I can't remember exactly what the answer is, but you get the idea. By the way, just to let you know, if they asked you for the magnitude of the acceleration vector, you could do that as well, and it would be the same deal, the square root of, in this case, 12 squared plus 2 squared, which is the square root of 148, etc., which I'm sure can be simplified further, ... I'll let you do that part. All right, so we've got a good idea of how to use the derivative. Now let's look at our final application, which is integration. Integrating a vector-valued function begins by integrating x of t and y of t. We're going to find, to our surprise and delight, that once again, it's very simple to use integration on a vector-valued function. Essentially, if this is our vector-valued function, the integral of it is the integral of each of the component functions, the x of t function and the y of t function. So let's do that in this first example. If I want to integrate my vector-valued function, dt, from 0 to pi over 2, then that is going to be the integral of cosine 2t dt from 0 to pi over 2. I should put this in the vector brackets, comma, the integral from 0 to pi over 2 of sine t dt. So we just integrate each of these functions. Now for cosine 2t, I'll need to put a 2 here and a 1/2 on the outside. And then when I integrate this, I end up with 1/2 sine 2t from 0 to pi over 2. And then over here, it's just going to be negative cosine of t from 0 to pi over 2. When I put pi over 2 in for t here, this becomes sine of pi, which is 0. Putting 0 in is also 0, so this component is 0. Over here, when I put pi over t in for cosine, this ends up being negative cosine of pi over 2, which is actually 0, minus a negative cosine of 0. This is 0 then plus cosine of 0, which is 1, so the y component is 1, and that's your answer. We have one more example using integration. Notice it says the acceleration vector of a particle at any time t greater than or equal to 0 is given by this function. If at time t equals 0, its velocity is I plus j, and its displacement is 0, find the functions for position and velocity at any time t. So now we're going to use integration to take us from acceleration to velocity and back to position or displacement. And because when you integrate you have the constant of integration, they've given us initial conditions. At time t equals 0, velocity is I plus j, and at time t equals 0, position is 0. So we'll use these initial conditions to solve for the constant of integration as we go backwards in time, or backwards, integrating backwards to those functions. So for this, I'm going to use the other form of the velocity vector valued functions. So for me to take the integral of a of t dt, vector a of t dt, I'm going to take the integral of this function, e to the t I hat plus e to the 2t j hat dt. Okay, this is just using the other notation, and you'll see why in just a moment. Now integrating this gives me e to the t, again the unit vector I, plus, and since this is e to the 2t, I would have needed a t, which means 1/2 on the outside, 1/2 e to the 2t j hat plus c. Now this is v. Okay, this is my velocity vector. Now to solve for c, I'm going to use the initial condition which said that when t is equal to 0, so I'll put 0 in for both of those t's, my velocity was I plus j. Now I'm going to kind of have to make room for this. This is going to be I plus j is the velocity at time t equals 0, which means e to the 0 I hat plus 1/2 e to the 0 j hat plus c. So we end up with I plus j is equal to, I'll just quit the hats for now, I plus 1/2 j plus c, because e to the 0 of course is 1. So when I subtract all this over to solve for c, the i's disappear, but I'll have 1j minus 1/2 j, which is 1/2 j is equal to c. That's my constant. Now let's rewrite my velocity vector, putting the constant 1/2 j in for c. But because the constant has a j in it, I'm going to combine it with this quantity, which also has a j in it. So in other words, I'm going to say 1/2 e to the 2t j hat plus 1/2 j hat. But let's just put them all together with their j hats. 1 e to the 2t plus 1/2 j hat. Okay? So my velocity vector with c solved for is going to be e to the t I hat plus 1/2 e to the 2t plus 1/2, and of course there's other ways you can write this as well, j hat. So you kind of have seen that when we're solving for the constant of integration, it might have some I components or some j components, but when I put it all together in the function, I'm going to combine that constant with whichever function is corresponding to the I or the j component. Okay, so we found the velocity vector. Now we have to integrate again to get the position vector. Now I'm going to start down here, but I'm probably going to have to go off to the side over here a little bit as well. But we're going to integrate these two, and this is going to be then this whole function dt, as you can see. So that means my position function, s vector, is equal to e to the t. It's really nice to be doing exponential functions here since they're so easy to integrate. And then this is going to be, I'm going to integrate this and also just distribute the j hat to each of these pieces right now. Again, we would need a 2 here, which means another 1/2 on the outside, 1/4 e to the 2t j hat, and then plus 1/2 t j hat plus c. Okay, so we have the indefinite integral, but we want a specific integral because we were given that at time t equals 0, displacement is 0. So let's go use that information up here. I feel like I should have some things written down and circled, but maybe I'll finish that way. 0 is equal to e to the 0 I hat plus 1/4 e to the 0 j hat plus 1/2 times just 0 j hat plus c. Okay, so we're not really going to worry about that term since that's 0, but now I have 0 is equal to I hat plus 1/2 j hat plus c. Now when I subtract those over to solve for c, I get negative I hat minus 1/2 j hat. Okay, this is my constant of integration for the position function. Now again, I want you to notice that what I'm going to do is break this up into the two component parts and combine it with the function that's already associated with that component. So in other words, this is going to be e to the t I hat, but also minus 1 I hat. Put that over there. And then for the j components, I have, of course, 1/4 e to the 2t j hat plus 1/2 t j hat, but now I also have minus 1/2 j hat. So I'm splitting this constant of integration into the two component parts and combining it that way. Now my final position function then can be written like this. I think I should end with purple. I'm going to have s position is equal to, we'll put in parentheses, e to the t minus 1 I hat, and then plus, and again all of this could probably be combined a little bit better, 1/4 e to the t 2t, plus 1/2 t minus 1/2 j hat right there. Okay, so that's my position function. Hopefully you can see that little j over there. I'll rewrite the vector function since I kind of messed it up when I put the integral symbols, but that was e to the t I hat plus 1/2 e to the 2t plus 1/2 j hat. Fun stuff right there, boys and girls. And that's your answer. Okay, we have finished our lecture on vectors, and there's your last page. Everyone needs a fake ID, right? Homework, see Edmodo for details, and that's it.